Hello, everybody. This is Miss Peachy from WCA Physics, and I'm looking here at Unit 4, Lesson 7 on Newton's third law. So I really wanted to make sure that I kind of walked you through this one. It's a very conceptual lesson, so there isn't a lot of math. And I did tell you at one point that if there wasn't a lot of math, then I probably wouldn't make a recording for it. But I felt like that this was a good one to make a recording for, simply because of the potential for misconception that takes place in this lesson. So I'm just going to move this over a little bit here. Here we go. So this lesson is talking about Newton's third law. We've talked about first law and second law already, and how the second law is a kind of a just mathematical description of the first law. In this case, we are looking for paired forces. And you've probably heard of Newton's third law as being described as for every action, there is an equal and opposite reaction. And a lot of times people explain Newton's third law and the examples they give are incorrect for Newton's third law. And so it leads to some misconceptions and some miscommunication. So let's talk about what this actually means and what it doesn't mean, okay? So our key terms here are contact force, free body diagram, Newton's second law, Newton's third law, normal force, pair forces, reference frame, system vector, and weight. All right, so um, as it intros into Newton's second law, which describes motion of a single object upon which a force is exerted. In the next level of complexity, we consider symmetry of pair forces in what's called Newton's third law. So when we look at two objects that interact, then we can look at paired forces. And the example they're giving is if I put a brick on a table. So if I have a brick on a table, here's my table. Okay, there's my table. There's my brick on it. Kind of a poorly drawn brick. But we can look at the force of the brick on the table, and we can look at the force of the table on the brick. So we have two objects here. The force that the brick is applying to the table and the force that the table is applying to the brick. So we know that these forces are equal and opposite. And we just know this because of Newton's third law. So be very careful in thinking that they need to be, in an unmoving system for this to be true. That's not true. What we need to see is that always, 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 according to Newton's third law, these two forces will be equal and opposite regardless. So the force on the brick and the force on the table are equal and opposite to each other. The brick exerts a certain force on the table based on the weight of the brick. So we have the brick's force, and I'll just draw this over here with a box. The brick has a downward force equal to the weight of the brick. And the force of the table exerts an upward force equal to an opposite, which we call the normal force. They are equal and opposite, but they are on different objects. And that's really the key to understanding Newton's third law. Those equal and opposite forces are applied to different objects. And the reason why that becomes important is because if you don't think of it that way, you're going to have miscommunication, misconceptions. Let's take, for example, we have some ice here. Whoa. Okay, let's do that one again. We have some, I'm doing it again. What's going on here? Just try to draw on the screen, man. There we go. We have some ice, and there's a wall right here, okay? And say we have a skater What an awful looking skater. We'll try that again. With some ice skates on. And he or she is going to push on that wall. So the skater pushes on the wall. That's one of our forces. Force of the skater pushing on the wall. And then we have the force of the wall pushing on the skater. So wall pushes on skater, skater pushes on wall. So these forces, are they the same or are they unbalanced? In the past, you might have been led to believe that these two forces are unbalanced because from experience we know that when the skater pushes on the wall, that skater is going to move. She's going to go flying across the ice in that direction. And because there's movement, you might be tempted to believe that there are not equal and opposite forces in this situation, but you would be incorrect. Because according to Newton's third law, for every action, there is an equal and opposite reaction. And so you might be scratching your head at this point and thinking, well, that doesn't make any sense because I know that in order for motion to occur, forces need to be unbalanced. So how can both of these statements be true? How can you both have equal and opposite forces and unbalanced forces at the same time? And so the confusion is, where are these forces applying themselves? So we have to look at our reference frames. We have to be able to look at where these forces are being applied. So Newton's third law specifically deals with two different objects. So we look at the force on one object and then the force on the other object when they are in contact with each other. So the force of the wall on the person and the force of the person on the wall are in fact equal and opposite. If we look at just the forces on the person and not the wall, what we end up with is a different situation. On the person, we have the force of the normal force of the wall pushing on the person, right? That's a force on the person. The force the person applies to the wall isn't on the person, it's on the wall. So we can't look at that one. The other force that we have is the force of friction between the person's feet and the ice. And in this situation, the force of friction is in the opposite direction, but it is smaller than the force of the wall pushing on the person. Because the force of friction is smaller than the normal force that the wall pushes, you fly across the ice going in the right direction because the forces on the person are unbalanced. But the force of the person pushing on the wall and the force of the wall pushing on the person are in fact equal and opposite. So these things can exist in harmony. Just because Newton's third law exists doesn't mean no motion can ever take place, right? Because I feel like people get confused about that because it doesn't make sense because we're not looking at them correctly. We need to only look at um, the forces on an individual object when you're drawing these free body diagrams. You can't look at all the forces in the system. Just look at the ones that apply to that individual object. In this situation, it's just the person. When we're looking at force pairs, when we're looking at Newton's third law, then we look at the force on the one object and then the force on the other object that they apply to each other. And according to Newton's third law, those are equal and opposite. I push on the wall pushes back at me with an equal and opposite force. So hopefully that clears things up a little bit. You understand the difference between force pairs and Newton's third law and how you can isolate forces on an individual object when drawing a free body diagram and show that those forces in fact are and can be unbalanced and result in the motion of the object. So if you have any questions on that, let me know, but that is kind of what you're going to be learning in this lesson.